Hi everyone and welcome to another lecture. Today we want to see how we can use Mathematica to simulate the heat equation, which is a second order partial differential equation. So the heat equation will describe how heat flows in a certain dimensional manner. That is, if you consider a two-dimensional case, then you will have, let's say, the coordinates are x and y. So the function that will represent the heat flow will come from a two-dimensional flow of heat that might represent heat flowing through a box or a cylinder or any kind of thing that you want, and those kind of things will be discussed in this video. So let's get started. So first off, we want to write our equation, that is the heat equation. So let's call it equation EQN, and it's first order in time. So let me just type D here. U will represent our heat and it will be a function of t comma x comma y, and we'll have a derivative with respect to t. This will be equal to, let's say, now I can have some coefficients if I want. So let's call coefficient 2, and here you will have a second order derivative for u, that is t comma x comma y, and now you want to have the second derivative. So it's just converting our symbolic expression into the mathematical language using the D operator. And after that, let's say I have another coefficient as, let's take this to be 1, so just type D u of t x y, and now you want to take the second derivative with respect to y. So this is it, this is our heat equation. So let's run it. Mathematica now knows what is equation is, and now we want to construct a solution. Now when it comes to partial differential equations, using NDSolve, that is a numerical solution, is often better than using the DSolve thing, because DSolve might take a lot of time. Also sometimes it's quite impossible to solve partial differential equations exactly, and it will totally depend on the problem itself. If the problem is simple enough, you can just go with DSolve, and if the problem is very complicated, it's better to stick with NDSolve. So I'll just go with NDSolve here, use NDSolve, and inside we are putting our equation. Then I want to put my initial conditions as well. So the first initial condition we want to impose is on t. So when t equals to 0, there is no heat flowing through this two-dimensional surface or a two-dimensional plane, whatever you want to call it. So let's take this to be 0, and we want to have this surface at dimension of 5 cross 5. That is, in the x-axis it will have let's say 5 units of length, and in the y-axis it will also have a 5 units of length. So think of a three-dimensional box, but the heat is coming from one side, and that side is just a square, and that square is a 5 by 5 square. So let's run it down over here. So let's say u of t 0 y. So this is where x equals to 0, right? So when this x equals to 0, what we want to have is some function that will depend on time. So think of it like this, that the box is some wrapped up into something, and two sides of the box are open in the environment. So you can take this to be, I don't know, let's call it an exponential function, and t. So this means the outside temperature is increasing exponentially when x is 0, that is at the 0 point. And now we want to fix another boundary condition for the final x point. So let's say this is now u of t comma 5 comma y, and let's set this to be 0. And you can easily see that if I take it to be 0, it kind of doesn't make sense. So you can also go with t, that is, or you can just take some other function, or you can just treat it to be constant as well. So let's treat this as a constant, and let's take this to be 2. Just for the sake of simplicity, you can also go with any function that you want, that is a function of t, since it will tell us about the temperature. And then we are done for t, and now we have to we are also done with x, so now you have to specify boundary conditions for y. So the first thing we want to do is that we want to specify t comma x comma 0, that is when y equals to 0. Let's take it to be as variant temperature, that is a sine function. That is, the temperature at this point is fluctuating sinusoidally, and again when y will be 5, that is t comma x comma 5, this will be equals to, let's say, 0, or you can also take another constant if you want to. So we are going with 0, and we are done technically. So as you can see that I have written down my equation, my boundary conditions, and after that I have to tell and solve that what are the intervals that I'll be working with. So since we are working with a rectangular surface, so x and y should go from 0 to 5 only, and for the time I want to see what is happening from time 0, that is the start of my experiment, to time equals to 20 units. So let me see if Mathematica can generate anything out of this. So as you can see that Mathematica is telling me boundary condition and initial conditions are inconsistent. So that's a thing you have to look at, since I have taken a fake example here because I am already making things up. So let me see if I can just make it consistent. So instead of exp, let's just call it 2. Again, it's saying boundary and initial conditions are inconsistent. So why don't we take this to be zeros? So let's take this to be 0, and also we have to make some changes in elsewhere. Let's see which boundary condition that will satisfy this whole thing. So I'm also taking when this is 5, this is just 0 as well, and I'm taking when x equals to 5, this is 2. So let's take this to be 0 as well. Sine of t, okay, and yeah, that's about it, right? So let's see. Now I have something. Now there is no inconsistency. But to make things more interesting, what you can do right now is that you can take this 0 to be as another function. So the problem has to be well defined, and you can see that I'm getting an interpolating function. So let's try to see what comes out of this thing. So let's suppress it, and now we want to plot it. So before you plot, what you need to do is that you need to, as again what we did in our earlier lectures, that you have t underscore x underscore y underscore, and I need to replace the solution that is coming out of sol. So type sol, sorry, not sol, u of t, x and y, and you want to replace it with the solution that is coming out of sol. So if you replace it, yeah, this is working. So let's now try to plot this thing. To plot it, you have to type plot 3D, and first we're going to take a fixed t and see what happens. That is, the solution is working or not. That is the method we are using, whether that will work. So type, instead of t, let's type 2, or let's call it, let's just type 3. I want to see what happens at 3. It will have x, it will have y, and then I want to have my x from -5 to -6 to 6. I want to have my y -6 to 6. Also, I think Mathematica will give us a warning that -6 to 6 will fall outside the range of the interpolating function. So yeah, as you can see, lies outside the range of data in the interpolating function. So even if you input this kind of range, Mathematica will use extrapolation. As you can see over here, extrapolation will be used. So Mathematica extrapolated the whole thing and gave us a result. So now what we want to do is that we want to animate what happens in time. That is, we want a dynamic solution. That is, we are running a simulation of this whole thing, and after you animate, let's just replace it with t, and now you want to vary t. So t from 0 to, let's say, 19.5. so towards the end, or you can just go for 20 as well. So let's run it. So as you can see that there is this animation, but at the same time we are getting a red, that is interpolation function lies outside the data range, that is this -6 and 6. So let me just pause it over here and let me generate a clean graph, and let's say I want to have 1. Since it starts from 0, so let's start from 0.5 and let's see up to 4.5. Similarly for y, you can also take different range that lies within your interpolation range. So I'm just going with 4.5, and let's see. Yeah, that's a nice animation, but we want something more, because seeing this graph, it's not clear to us that how is heat flowing or what is happening with the heat itself. So what we want to do now is that we want to use a color function. If you use color function, then you can go for temperature map. Okay, so I think I made a mistake. Temperature map is not recognized as an option. Alright, so let's see how we can fix it. The way to fix it is to, okay, so we typed the color function inside animate, so it shouldn't be there, it should be inside the plot itself. So just type again color function, and now you can see there are no red marks and we are technically good. If you do it, alright, so now there is a very nice map. And also I want my plot to be detailed, so just go for plot theme detailed over here, and also let's go with animation running false, and yeah, so the plot theme detailed here is not doing us much good. We want to have this details of our colors, that is which color is meaning what. So in general, if you go to color data, so let me just type again something called a color data over here. If you just press it or click on the information button, you can see this color data will come with a scheme and a property. And you can see that for temperature map, this is the thing, that is whenever there is low temperature, there is blue, almost zero temperature is white, and for the red it's the hot zone, that is where the temperature is very hot. So, and here you can see always a command that is plot a surface with gradient colors. So you can see that the way to use this data would be to, that is the data over here would be to write as this. You have to type this color function, then color data, then what kind of scheme you want, and finally this hashtag 3 for a plot 3D will construct a peer function and AND. So it will plot this function over here with this data, and that is indicated by this hashtag 3 and AND. So let's try to see it, what happens. So just get rid of this color data, and instead of color function, let's go for this. Okay, so there will be a first bracket over here and everything looks good. Now let's try to move this bar, and this is much nicer than before. And yeah, this is how you can simulate the heat equation with different boundary conditions. And as you can see, as I run this animation, there is this ranges over here, so they are fluctuating, and that is on the z-axis. So what I can do right now is that I can specify a plot range, and that plot range will fix whatever the numbers that were fluctuating over there. So let's try to do it. So to fix the plot range, what you need to do here is that apart from these guys, you need to have plot range let's say -2 to 2. And now if you run this thing, yeah, now there is no fluctuation over here. So yeah, this is how you can see what is happening in the heat equation and what is happening with our heat functions, or how the heat is flowing. Also note that, as I mentioned earlier, that this is kind of a fake example, so that's why all these things are not very well distributed. But for real life problems, the boundary conditions and the initial conditions are very well specified, so you can also do things with that. But before we finish off, let's try to see that if I had exp of t like this, let's see what happens. Let's run this whole cell together, and you can see that boundary conditions and initial conditions are inconsistent. But now if you play it, see, if they are inconsistent, this is the thing that will happen, that is, there is no solution. So the surface is just gone, just like that. So up until this point, it could show us something, but after a certain time, it was gone. So instead of t, why don't you take something else? Because exp, when t equals to 0, we are saying this is equals to 0, but here that's not the case. So instead of that, let's take t squared minus t. Now let's try to run this, and now there is no problem. You run it, but again you can see that after some time it's just vanishing. So these are the things one needs to take care of very carefully, that whether or not these boundary conditions and the initial conditions are consistent or not. And Mathematica will actually tell you that whether your boundary and initial conditions are consistent. And this is this surface looks like a fluctuating heating surface where the temperature is varying very rapidly. So this will be it for today, and I'll see you guys on the next lecture. And hopefully in the next lecture we'll try to cover the wave equation. That is another important partial differential equation. So thank you.